Lecture today, Professor?
Yep, lecture today.
That's what they're like.
Hi, Sam.
Take a picture of your notes if that's okay, because I just want to see
These ones?
yeah. Screw posts. Not asking for shit. I'm good. Sure, you're for 200 square foot of pre-preg garden. This is.
All right, it's 5:30. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Okay.
Okay, good. Better than bad. So good. Okay. Hopefully everyone enjoyed the second ANSYS activity on Tuesday. So that's going to be due next week. And then next week we're actually going to have our next activity again. So our ANSYS activity number 3 is planned for next Thursday. So 1 week from today. So I have a lecture planned for today, I have a lecture planned for Tuesday, and then on next Thursday, we'll have ANSYS activity 3. And by that time, we'll be all kind of caught up on the schedule of ANSYS activities. Okay, and another thing that you should be preparing for soon, so I think probably not next week, but probably the week after that, I will introduce to you guys the midterm project. So the midterm project, I always like to introduce kind of at the end of September. And then you guys, I give you guys about a month to work on it, and then it's going to be due by not Thanksgiving, Halloween. So the idea with the project is that I'm going to give you a part, and so I'm going to give you a CAD model. You'll have a choice of 3 different CAD models to choose from, and then you're going to run a full finite element analysis. Okay. So by the time at this point we've done ANSYS twice, and so I think we're still kind of getting to know the software. After you do ANSYS activity 3, then you'll have covered all the basics of ANSYS, and so you should be able to take everything you learned from the first 3 activities and apply them towards the project. Okay, but we'll talk about the project. Probably not next Tuesday, not next Tuesday, but a week from next Tuesday after we do activity. Okay, but I just wanted to kind of mention it just to put it on your radar. Okay, so the lecture notes today are going to be on material properties, and so this is kind of the third important aspect of FEA. So we've already done meshing, we've already done boundary condition, and so material properties are kind of the last thing. Okay, and I will say that we're only going to be talking about material properties for a day, but honestly, you could probably spend an entire semester talking about different material modes. So we're giving it a very basic treatment. There's really a lot more to learn here, and ANSYS actually has a very robust material library. Not only library, but they contain a lot of different material models as well. So we're only barely scratching the surface for material properties, and that's not a choice that I'm making because I think material properties aren't important. They're very important. It's just that there's just so much other stuff we need to cover in this class, and so one lecture is all. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So the topic for today is material properties. And let me say this too, that I know that the kind of the focus and kind of the fun parts of this class are the ANSYS activities, but all of these lectures play an important role. I'm not just doing these lectures just to fill time, in between the ANSYS activities, right? Because one thing that we're going to talk about on the project is that doing a finite element study is more than just kind of putting a part into ANSYS and then running the simulation and getting some nice screenshots. It goes beyond that, and so the biggest struggle that you're going to have as someone who works in finite elements, something that I struggle with all the time, is not really in doing the simulation, Doing the simulation is the fun part. The hard part of doing finite elements is actually convincing other people that what you did was correct, right? Because the thing with simulation work, because it's so easy, it's not easy. There's the barrier to entry is lower compared to running an experiment. It's very easy to mess it up, right? It's very easy to use the wrong boundary conditions or to use a mesh that's not good or to use the wrong material properties or the wrong material model, right? And so the majority of your time that you're gonna spend, working in finite elements is not in doing the work yourself, it's in convincing other people that what you actually did was legit, okay? And so that's kind of the purpose of all these lectures is to understand kind of what thought process, what thought processes go into, how you select the meshing, how you select the boundary condition, so that you can, use that information to justify your decisions in finite elements, okay? So that's something we're gonna talk about for the project, in about a week and a half, that, when I grade you on your project, only a small fraction of the points, maybe about 30% of the points are gonna be on the results themselves. The majority of the points are gonna be is that, do you really understand, why you did the meshing the way you did? Do you really understand why you chose the boundary conditions what you did? Do you really understand kind of why you chose the material properties the way that you did? Okay. And so the justification and how you justify it, that's where most of the points are gonna be. And so, that's kind of the purpose of all these lectures. Okay, so what are material properties? So material properties is kind of the general term that I use to refer to all of the physical parameters of the material that affect how it responds to exterior load. Okay. So the way I like to think about material properties is that, oftentimes when you're tasked with, describing a material or describing a part, and you're not allowed to use the name of the material itself. So let's say that you're trying to describe aluminum to someone without using the word aluminum, right? Probably what you'll do is you would describe its material properties. So you would describe what its Young's modulus is, what its density is, what its Poisson's ratio is, what its yield strength is, right? And so it's all the things that you would describe a property with without using its actual name. Okay. And so, you guys understand this, right? You've worked with material properties a lot. You know that every material has a set of properties that differentiates it from another material, right? So it's not really anything, you guys know this already. It's just kind of saying probably what you already know in a different way. Okay. All right. Mathematically, these material properties are important because they influence the governing equations. And without going into specifics or without kind of writing the equations themselves, usually when you see a material property in a governing equation, it usually acts as a proportionality constant. So it acts as a coefficient to certain terms in the equation. And so depending on the values of the material properties, they may cause certain behaviors in the equation to be more pronounced than others. Okay. Okay, and so just like with the meshing, just like with the boundary condition, in order for your finite element simulation to be accurate and reliable, you need to select the proper material or the proper material properties that model your physical system.
Bless you.
Okay. And so whatever material your physical part is made out of, you need to make sure you import that into ANSYS or import that into your software. Okay. And so we did a little bit of this on Tuesday, right? So when we did our ANSYS activity 2, we changed our material to aluminum. And the way that we did that was we created a new material, we input its Young's modulus, we input its Poisson's ratio, and then that affected the response of the system. Okay. If you ran the exact same simulation, so let's say that you applied your fixed constraint, you applied your mesh, you applied your 100-pound loading and bending on the bike crank, but instead you made the bike crank out of, I don't know, let's say plastic, you're going to get a very different result, right? So you're going to get much more deformation, much more stress in that case. Okay. And so it's really important that you pick the right material property for your simulation. It seems obvious, but it has to be said. But compared to the boundary conditions and compared to the meshing, for most people, the material properties is probably what you spend the least amount of thought into, or the least amount of time. And the reason for that is that, a lot of modern softwares often make it very, very easy to choose materials. And if you're using a material that's quite common, that's within, the material libraries of a lot of these softwares, it is very simple. And so you just click a button, and then aluminum's there, copper is there, steel is there, right? So for most common materials, it is very easy to choose the right material because it's kind of already preloaded into the software. But what if you're not using a common material? Right? One question I get a lot for the final projects is, can I do a finite element simulation on a 3D printed part, right? So 3D printing part, it's first of all, the materials that you use for 3D printing are oftentimes not metal, so they're oftentimes some kind of plastic, and so that's going to have very unique properties. But also, what's unique about 3D printing is that usually 3D printing your parts are constructed layer by layer, right? And so whatever layer, whichever direction is perpendicular to those layers, that's going to have very different properties than the direction that's kind of parallel to those layers, right? And so it's important to really have a good understanding of what tools are available to you in ANSYS for specified materials, so that if you do have a situation where you're using maybe like a carbon fiber or something like that, or maybe you're using 3D printing, right? You'll know kind of what tools are available to you. Because I guarantee you that if you're trying to model a 3D printed part and you model as an isotropic material, even if you got the Young's modulus of the plastic material correct, right? If you're not accounting for the layers, you're going to get a result that's not going to be accurate at all. And so if you put that part into practice, it's going to end up breaking, and then you're going to be kind of more in trouble. Okay. So that's kind of the purpose of the lecture today. So the purpose of the lecture is kind of two parts. Where on the one hand, I want to go over a little bit more of linear elasticity, just to kind of really nail it in. I feel like we probably talked about it twice already in the class. But also just letting you know, what are some other common material property, material models that are out there, what are their applications, and how do you actually specify those things. All right. Any questions on this before we move forward? Okay. All right. So let's start again with linear elasticity. So again, linear elasticity is the material model we're going to use most commonly in this class, just because it's the easiest. It requires the least amount of parameters. Okay. And so in linear elasticity, these are situations where the stress in the part is linearly related to the strain that's induced. Okay. So most metals kind of fall into this category. The reason being is that metals have a very kind of orderly kind of molecular structure, and so they tend to have nice kind of linear relationship between stress and strain. Not only that, but it's also isotropic. And we'll go over what that means in a bit. Okay, but for linear elasticity, you've probably seen this curve a bajillion times at this point, right? We have strain on the horizontal axis. We have stress on the vertical axis. And their relationship is purely linear. Okay, so what are the parameters for linear elasticity? So the first parameter, probably the one that everyone thinks of when they think of linear elasticity, is the Young's modulus, otherwise known as the elastic modulus. So Young's modulus, we give that the symbol E. So Young's modulus is the slope of the stress strain curve. And what the Young's modulus expresses kind of in a qualitative description way, it describes how well this material can resist deforming when in the presence of external loads. And of course, higher values of the Young's modulus means that, this material can better resist deformations, right? And so materials that we associate with higher Young's moduli, those are the stronger materials, right? Materials that require a lot more force before they start to bend and deform. So, the one parameter that really kind of encapsulates linear elasticity is the Young's modulus. And so that's usually the first thing that you look up, first thing that you think. All right. Second parameter that's associated with linear elasticity is the Poisson's ratio, which is strictly a multidimensional parameter. So Poisson's ratio is not relevant in 1D. So Poisson's ratio has the symbol nu. Okay, it's a Greek squiggly V. And so the Poisson's ratio measures how much the material will deform or how it will deform in directions that are perpendicular to the load. Right, so I think we talked about this when we did our review of mechanics, where whenever you deform a material, right, it's kind of changing in length or something like that because of conservation of mass, right? If a material is elongating in a certain direction, that means it has to get thinner in another direction in order to make sure that the mass is conserved. Okay, so the Poisson's ratio kind of describes how much or how well that this happens. Okay. So those two are, I would say, are the strictly required material properties, right? And so if you recall from activity 2, the two properties that we specified when we define our aluminum material properties with just the Young's modulus and the Poisson's ratio. Okay. Technically, there are other properties as well, but a lot of times we assume that we compute these other properties from these topics. Okay. So one example for this is the shear modulus. Shear modulus is not often talked about a lot. And so the symbol for the shear modulus is a capital G. Right, so it is a modulus parameter, and so it's very similar to the Young's modulus. Okay. Okay. And so the shear modulus is a parameter that measures how well the material can resist shear. Okay. And so it has the same units as the Young's modulus. It's just that it measures it differently. Okay. The reason we don't often specify the shear modulus is that for an isotropic material, you can compute the shear modulus from the Young's modulus and the Poisson ratio. We have this formula here, we have G is equal to E divided by 2 times quantity 1 plus E. The nice thing about ANSYS is that that formula is actually built into ANSYS automatically, and so, some of you may have noticed this in activity 2, when we were specifying the aluminum material property, there was an entry for shear modulus, there was a space for it in the material window, right? But as soon as you input the Young's modulus, as soon as you input the Poisson's ratio, the value for the shear modulus is automatically calculated based on this formula right here, okay? And so this is important too, and so we need to know how well our material will resist shear. It's just that for an isotropic material that is linearly elastic, we compute the shear modulus using these terms here. Okay. So oftentimes, we don't really concern ourselves with it, even though it is technically real. Okay. Any questions on this so far? Pretty straightforward. Okay. So this is not in my notes, and I'm actually surprised that I haven't put in my notes after all these years, but there is one more property that I do want to talk about at this point. It doesn't have anything to do with linear elasticity, but we are going to use it a lot in this class, and that is the yield strength. So oftentimes, yield strength, I've seen it given the symbol sigma a lot of the times, okay? So the yield strength describes, how much stress, or what's the highest amount of stress that your material can withstand before it starts to break or fail. Okay. So if you think back to our ANSYS activity 2, right? So we were kind of exposed to this in that activity, right? I told you in that activity that the aluminum that we were using to construct the bike had a yield strength of 35,000 psi. Okay. And so what you did in order to test whether your bike crank will fail is that you ran your simulation, you checked the equivalent stress, and if the maximum equivalent stress in the model exceeded, well, it was 35,000 divided by 2 because we had the factor of safety. If that exceeded that threshold, then your bike crank was in danger of failure. Okay. And so the yield strength, it doesn't exactly belong to linear elasticity, but I did want to mention it today just because we use it in activity 2. We're going to use it in activity 3 as well, and for one other activity when we simulate a car crash. Okay. So understanding the yield strength is it's important. Okay. All right. And one other thing I want to talk about for the yield strength before I forget is that because there's a lot of different stress metrics that are out there. Okay? Usually the one that we use to compare to yield strength is the equivalent stress. So that's the reason, we choose equivalent stress. You're going to see us use equivalent stress a lot in our activities. Again, because equivalent stress is a single metric, a single number that kind of summarizes all the different components of stress. So it's kind of the easiest one to kind of interpret. Okay. All right. So next topic that I want to talk about is the difference between isotropic and anisotropic materials. So most of the materials that we're gonna use in this class, if you're just using kind of basic, just static structural, or basic structural steel or basic aluminum, we assume those to be isotropic materials. And what that means basically is that, an isotropic material, isotropic is a term that's used to describe that, it doesn't matter which direction, right? It's gonna experience this, it's gonna exhibit the exact same properties, the exact same strength, no matter what direction that you move. Okay. So no matter if you compress it from the horizontal direction, if you compress it from the vertical direction, compress it from the front and back direction, you're still going to exhibit the same amount of stress. Okay. Now, of course, this is not talking about, the difference between bending or compression or tension, right? That was kind of what the end of activity 2 was about. I'm talking just, strictly just a compressive force in each of the directions. So the example that I like to give is that if you have a cube, okay? I guess if you have 3 cubes of the material, right? Okay. It doesn't matter if you load this cube left to right, right? So if you have forces that kind of act on the cube like this, you have forces that act on the cube like that, or you have forces that act on the cube like this. Okay. Okay. So in all 3 of these cases, we have compressive forces. And if we have a cube, then all sides are going to be the same size, right? It doesn't matter, which way we load it. You're going to get the same amount of compression in each of these situations. Okay. Or an isotropic material. Okay. All right. So when you can assume that your material is isotropic, it simplifies a lot of things for you because you don't have to worry about specifying strength in different directions. Okay. The good news is that most metals and especially most metals that we're going to work with in this class are considered isotropic. And again, the reason for that is that on a molecular scale or an atomic scale, the structure of a metal is very, very well structured, right? And so there's kind of, the space between the different molecules of metal are basically the same in every single direction. That means the molecular bonds between the different molecules are exactly the same in every direction. So it's nice. Okay. And if you are considering an isotropic linear material, right? So isotropy and linear elasticity are kind of separate things. But if you can assume both, then that means you only need 2 parameters to fully specify your material. And there's two parameters, we've already talked about. One is the Young's modulus. Two is the Poisson's ratio. Okay. And then other properties like the shared modulus, there's also another property called the bulk modulus. Those are computed directly from those two. Okay. All right. So, probably up to this point, if you think back to your strength and materials class, this is kind of where you stopped, right? And so you think, two material properties, that's enough, right? Well, it gets worse than this. So, the fact that I made this a sentence, the fact that I had to write down, only two parameters is that it gets a lot more hairy than this. And we'll get into that in a second. But before we do that, are there any questions on this? Okay. So let's talk about, what if you don't have an isotropic material? Some materials will exhibit different amounts of strength or different rigidity in different directions depending on how you load it. Okay. So probably the most common example, and this is an example that probably a lot of you will be doing in your project, is any kind of wood material. So wood, assuming that the wood came from a tree, right? It wasn't just particle board that was just mashed. It's not just mashed together sawdust, right? So wood that comes from a tree has fibers that run through the material that correspond to the veins and the fibers of the tree that it came from. And of course, those fibers have a specific direction. And so depending on if your loading is going to be in the same direction as the fibers, or maybe your loading is perpendicular to the fibers, you're going to experience or observe different strength depending on that direction. And so generally speaking, when you have a material that has these kind of fibers running through it, if you load it in the same direction as those fibers, you're going to get a much more strength. It's the same idea that kind of goes behind reinforced concrete as well, right? And so a lot of times, you'll see kind of freeway kind of support columns. They're not only made of concrete, but they also have kind of these steel wires or steel beams kind of running through them as well, right? You see them in kind of the concrete blocks that prevent you from going over a cliff, right? And so the idea is that if you load the columns, if you load the structure in the direction of those fibers, it's going to increase the strength. Another really common example that you see is 3D printed parts. So like I mentioned in the beginning of class today, 3D printed parts, a lot of them are kind of based on technology where you kind of build the part up layer by layer, right? And so the strength in that direction, right? And so whichever direction is perpendicular to the layers, that strength is really dependent on how one layer can kind of bond with the other one. knowing that, there's some delay in terms of, when you place the first layer, then the head of the printer kind of goes around and comes back, right? A lot of that strength, it depends on how well those layers can kind of stick together. Okay. And so generally speaking, the direction that's perpendicular to the layers will exhibit less strength than the other directions. So that's just two examples, but there's a lot more out there. I think probably one material that's common as well is carbon fiber, right? Carbon fiber has that kind of honeycomb. Carbon fiber has that kind of honeycomb structure on the inside that's going to affect the strength in certain directions. If you have any kind of composite material, that's going to affect its strength in different directions, and even so some examples from my own research is that if you have biological materials like cells or tissue or something like that. Those are going to be very weird materials too that don't kind of conform to the isotropic elasticity. Okay. And so, if you're working with these kinds of materials and you want to simulate them in ANSYS, this kind of behavior is something that you really want to capture, right? And so if you don't capture these properties, if you assume that it's an isotropic material, your results are going to be pretty off, most likely. Okay. And so to capture these, you need new material models. So you need to go beyond the linear elastic isotropic material. Okay. And in truth, there are literally dozens of different material models that you can use. We don't have time in the class to kind of go through all of them. But I'm going to give you a couple here that are probably most common and honestly probably the easiest to implement. Okay. So the first type of material that you can specify is known as an orthotropic material. And so we call any simulation that uses orthotropic material models orthotropic elasticity. Okay. And so in orthotropic elasticity, what you're going to specify is you need to specify the strength of the material in each of the three Cartesian directions. You can specify the strength in the X direction, strength in the Y direction, strength in the Z direction. Okay. You also have to specify, so that's three values of Young's modulus that you have to specify. You also have to specify three values of the Poisson's ratio. And the reason for that is that you need to specify kind of the interactions of the deformations in between X and Y, X and Z, and Y and Z. because you're kind of you're kind of loosening up this this assumption of isotropic materials, you need to specify these interactions. Okay. And another thing that you have to specify is that because you no longer have an isotropic material, you're gonna have 3 different values of the Young's modulus, 3 different values of the Poisson's ratio. That formula that we showed earlier for the shear modulus no longer applies in this case at all. Okay. And so in addition to these so far 6 parameters, you need to specify 3 more shear moduli for each direction as well. And so in total, right, if you count this up, we have 3 Young's moduli, 3 Poisson's ratio, 3 shear moduli. That's 9 parameters that we have to specify in total for this material. So that's a lot more, right? And what's difficult about using orthotropic elasticity is that there are some materials where there's documentation online about which what value to put for these 9 parameters. And so if you're able to find that for your material, then you're golden, right? So there's not really you just input that in. But getting data for orthotropic materials is starts to get a little bit difficult. Just because that orthotropic elasticity is kind of one of the more simple ways to kind of model different different strengths in different directions. And so even the people who have done tests, and so maybe scientists have done biaxial testing on like balsa wood, right? They may have input their data using a different material model as well, right? And so the main difficulty with these types of materials is actually looking up and finding the values of the parameters that you should put in. But it's important to kind of specify. All right, any questions on this so far? Okay, so that's orthotropic elasticity. So some of you will use this in your final projects. There are some materials that do have some data out there that's easy to get. Okay. All right, so kind of in the same realm, and so kind of a generalization of orthotropic elasticity is we have anisotropic elasticity. So anisotropic elasticity is a further generalization. And so orthotropic elasticity is a generalization of isotropic, where some of the assumptions that we use to in isotropic elasticity are kind of lifted. But even with orthotropic elasticity, there are still a significant amount of assumptions that we make in the governing equations. Okay. Anisotropic elasticity is the most general framework, so no assumptions have been made about the behavior of the material. Maybe you guys kind of talk about this in the strength materials, but there's a significant amount of symmetry assumptions that are made. But if you don't make any symmetry assumptions and you just go by pure anisotropic elasticity, you need 27 different parameters in order to specify this material. And so if you think back to your strength of materials class, the stiffness or the Young's modulus really there's a four-dimensional tensor that's used to describe the stiffness of material, right? So through a lot of assumptions of symmetry and things like that, we usually get that down to one parameter, which is just the Young's modulus. But if you don't do anything, so you stick with the four-dimensional tensor, you still end up with 27 different parameters, which obviously is not practical for most cases, right? So anisotropic elasticity is really only used for, I would say, kind of the most weird materials, to kind of put it in an all-encompassing way. So, the only ones that I've seen use anisotropic elasticity recently are mostly biological materials that have kind of cells and kind of living parts, and there's mechanotransduction on the inside there. So, any kind of material that has some kind of active or reactive component, that's usually what's used for anisotropic elasticity. For most, I would say passive engineering materials, then anisotropic elasticity is kind of overkill. And you're gonna have a hell of a time trying to find, a source that gives you all 27. Okay. So, for the most part in this class, we're going to use isotropic elasticity. If you're using material like wood or some kind of, ABS for 3D printing, probably you're going to go with orthotropic elasticity. But, I wanted to kind of illustrate to you that it goes far beyond this as well. All right, any questions on this? Okay. All right, so let's talk about plasticity next. All right, so while it's probably going to be uncommon for you to pick an orthotropic material or an anisotropic material, plasticity is something that probably should be accounted for in a lot of your simulations. Okay, so the idea with plasticity is that once the deformation in material kind of reaches past a certain threshold, the stress-strain relationship of that material starts to change. And so, you've probably all seen this curve as well, right? And so, for most materials, strain, stress. So for most materials, and I'm talking linearly elastic materials, the stress-strain relationship is linear up until a certain point, right? And so if your deformations are large enough such that you kind of exceed past this linear region, then you go into a region what's known as plastic deformation. Where the stress-strain relationship kind of follows this kind of square root or kind of this radical kind of behavior. Okay. And so this point where that stress-strain relationship starts to change, we often call this the elastic limit. And this region right here is the plastic deformation region. All right. So what are the characteristics of plastic deformation? Well, first of all, the stress-strain relationship starts to flatten, right? And so that once you kind of exceed that elastic limit, as you apply more stress, it's actually going to cause the strain to accelerate, okay? strain slash deformation accelerates with respect to increasing loads in the plastic deformation region. Okay. And so if you're in plastic deformation, you increase the load by a little bit, right? The strain is going to increase by a lot more. The other behavior that you see is what happens if you release the load, right? And so normally, if you're in just the linear region, right? And so let's say that you load a structure up to a certain point and then you release the load, right? As long as you're still within that linear region, by releasing the load, you return the material back to its resting state. Okay. So the resting state being no stress and no strain. But if you release the load from the plastic deformation region and you kind of let it rest, right? You're going to come back to a state that has some residual strain. So, probably the way that you've learned it before in your strength of materials class is that, once you kind of go to plastic deformation, some of the deformation will be permanent, right? Maybe not the full extent, but it's really hard to come back to the original state once you exceed plastic deformation. Okay. So visually, it looks something like this. And so let's say that you're loading material and you load it up to a point where you get into the plastic region right there. Okay. If you release the load from that point, then the stress is obviously going to go back down to zero, and the path that the material will take to in terms of the strain will have the exact same slope as the linear region. Okay, and so let's say that you release the load. The strain is going to come back down to this part right here, where the slope of this line is the same as the slope of that. Right? And so at this state right here at the bottom, right, there's no stress in the material. So that means there's no external loads being applied, right? But even with no external loads, you can see that our strain is non-zero. So this right here is our residual strain. But another thing kind of interestingly happens at this point too. So with that residual strain, you actually, even though the part is kind of permanently deformed, you also kind of strengthen the material a little bit as well, right? Because if you kind of follow this curve again, right? And we look at this point at the top. And so if we were to kind of release the load and then try to load it back up again, if we wanted to get back into the plastic deformation region, you can see that our elastic limit has actually increased. And that phenomenon where the elastic limit actually increases, as you get deeper and deeper into plastic deformation, that phenomenon is known as hardening. Okay. And in fact, that property or that quality of hardening is actually something that you have to specify. Okay. And so if you wanted to include plastic deformation in your ANSYS simulation, you also need to specify how the hardening behavior behaves as well, because there are some differences. And so if you expect that, the loads in your simulation are going to be relatively high, your deformation is going to be relatively high, then you need to specify some parameters with regards to the plastic deformation. Okay, one of them are the hardening rules. Okay, so there are two options mostly for this. So the first is known as kinematic hardening. Because what I've just shown you is kind of just like one-dimensional hardening, but in 3 dimensions, you have kind of a complex interaction between the 3 different directions. You also have tension and compression. Okay. And so the different hardening rules kind of describe, how the material, behaves in tension versus compression. Okay. Okay. So in kinematic hardening, what you're basically assuming is that the difference between the tensile yields of the tensile elastic limit and the compressive elastic limit are the same. And so basically what this means is that if you're hardening in one direction, so let's say that you gain some tensile strength, right? That means that's going to weaken your compressive strength. So that's kinematic hardening. The other type of hardening that's available to ANSYS, or I'd say the two most common ways of doing this is isotropic hardening. And so just like the name implies, remember isotropic basically means that, it doesn't really matter which direction that you do it in, okay? And so in isotropic hardening, basically what that assumes is that the elastic limits in all directions are all going to be the same. So if you harden in one direction, you strengthen in one direction, it's going to strengthen equally in all other directions. All right, and so the question then becomes, which one should you use? So typically, for metal that you've already kind of assumed that it's an isotropic material, you're using isotropic elasticity, then it's probably going to harden using isotropic rules as well. Okay. So for most of the materials that you're going to use in this class, isotropic hardening is probably going to be the one that that you're going to use. Okay. Kinematic hardening is usually for ironically speaking, plastic materials. Right? And so with kinematic hardening, those are materials that you expect that if you stretch it, then it's going to be much easier to compress it. So generally, those are kind of plastic materials. Viscoelastic materials are kind of like that as well. But for most engineering materials that are metals, then isotropic hardening is the one that you use. All right. Any questions on the hardening rules? Okay. All right. So last thing I want to talk about today is the specification of the plastic curve itself. Okay. And so I kind of drew just a generic kind of stress strain curve right here, right? So the behavior in the linear region is pretty well defined. Okay. And so all you need is a Young's modulus that tells you the slope, right? But once you get into the plastic deformation region, right, that stress strain relationship now becomes nonlinear. Right? And so you can't just describe it with a single parameter. Okay. And so, if you have a material that's already kind of built into ANSYS, hopefully, the stress strain curve should already kind of be included. But if you need to include the plastic deformation behavior yourself, there are different ways to specify kind of this plastic region. The difficulty with this is that it is a nonlinear relationship, and a lot of times you need kind of very specific kind of material testing data in order to get this, which is not available a lot of times. So there are a couple options that you have here, kind of depending on the quality of the data that you have. Okay. And I will say that, for these, we're kind of getting deep into the weeds right now of specifying plastic material properties. I would say the most common case where you would have to use this is, let's say that you work for an engineering company and you're using kind of a custom material that's proprietary and used in-house, right? And you have access to a lot of these kind of biaxial testing, material testing, right? Otherwise, this kind of information is a little bit hard to obtain, just kind of searching on it. Okay, but there's two options for this. And so one option is the bilinear stress strain curve. And so with the bilinear stress strain curve, what you're basically going to assume is that once you hit the plastic deformation region, you're again going to have linear stress strain relationship, but with a different slope. The stress strain relationship looks like the following. We have our initial kind of linear region right there. So that's usually kind of a steep curve. And then once you reach the elastic limit, you then follow a different path, which is again a linear path, but only has, only has one slope. Okay. So the benefits for this is that it's easier to specify. You only have to specify a second slope. The downside, of course, is that it may not be perfectly accurate because you're not getting that exact curve. Okay. Okay, and then the other option that you have, if you have a lot more data, is to take what's called the multilinear approach. And so in the multilinear case, you're going to specify different slopes in different regions, okay? So this will give you a greater degree of control, but of course, this is going to require a lot more data. So the stress strain relationship, in this situation may look something like this. You have kind of more data points like that, and you're able to kind of accommodate different changes in the curve. Okay. And so with the multilinear approach, you'll probably approach kind of true classic behavior, compared to the bilinear approach, but you just need to have the data to back. Okay. So one more thing, actually. So the last thing I want to talk about today is, how do you even access plastic deformation? Okay? Because by default, actually, plastic deformation is actually turned off in ANSYS. And so naturally what ANSYS will assume is that you'll have just linear elasticity for forever, okay? And so if we kind of draw out what ANSYS kind of assumes is that, basically you have this linear stress strain relationship and it just goes on for forever, okay? And so if you don't turn on plastic deformation, then, that's what ANSYS is going to assume. So as long as you kind of keep linearly increasing the amount of load, your deformation and strain will also linearly increase, okay? So to turn on plastic deformation in ANSYS, there's a setting that you can do, and it's usually in the simulation settings, and it's literally just a checkbox that you specify. You said you want to specify large deformations. And so if you turn that setting on for large deformations, then your simulation will start to account for plastic deformation. The reason it's turned off by default is that it is actually more expensive. It does complicate your governing equations quite significantly. And so just for cost reasons, actually, this may only be a thing in the student version or the academic version, just because the cost is limited. You can still enable it in the student versions and the academic versions, and you just have to turn it. Okay, but just be aware that if you're turning it on, it is going to make your simulation more expensive. So if you have a mesh with a lot of elements, that's kind of something to do. All right, any questions on anything we talked about today? Okay, all right, so that's all we got time for today. So thank you guys for coming today. Our next ANSYS activity will be a week from today, so next Thursday. And so make sure you guys show up for that. So thank you guys for coming today. I hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys on Tuesday.
I'm honestly just gonna finish my parts of project manager, and then I'm gonna work on the. Honestly, I'm just gonna put whatever and just add numbers, because we wanna test more, so we're like, okay.
No, same here. That's why I actually cheat 100 square feet an hour.
Oh, look at my final price is insane. And then like 15 gallons of plastic.
Oh, this one's mine.
I still don't know what the universe lifting bulb is. I've been trying to figure it out. It's annoying.
I feel so bad. I'm supposed to know everything about this rocket. I don't know half the things that go.
I love that. When you said that.
That's why you laughed.
Yeah.
Get studied.
The kindness between those, they.
I'll see you in Chuck's class.
Just go on. I got you, bro.
I know exactly.
He is not.
Are you guys?
Oh.
He doesn't have the, he doesn't have the countries in the list.
Oh, I see.
It's not whole row stress.
Yeah, I had very few people in optimization do that. Oh, we're in this semester. Come on. But it makes sense. If you guys.
Is that what David?
I just, do you know what's